my name is Xu Hongwei from National Simple Transportation Research Center. So I believe all of you already know the rules, so please follow the rules. So in the first beginning, I would like to ask all the people to introduce yourself and your team. So first for the reporter.
Okay, hello everyone, I'm the team leader of Team Verduri, and my name is Tong Wei Chen. Here's Chen Jianchang, Yang Liyu, Nan Guojun, and Zhou Jiachen. And we're very honored to have a conversation with you.
So next brother.
Hello everyone, I'm the captain of Geifenduo team. My name is Cai Bingyi. This is Xu Wei Chen. This is Su Yirui. This is Li Chenggang. This is He Yi. Thank you.
So for the reviewer.
Hi everyone, our team is Suyo. My name is Pen, he's Daniel, he's Jason, and he's Clyde.
Okay, now we would like to ask the judges to introduce yourself.
I am Xiaowei from National Central University.
I'm John Mao from National Dongwon University.
Yejin from the State University.
Okay, so because you already choose the project, so now you have 5 minutes. Oh, good, right? Please write the name to the backboard.
Okay, hello everyone, I'm the reporter from Team Verduri. Today my topic is water bottle for tea, water bottle rockets. For a public statement, pump air into a plastic water bottle partially filled with water. Under certain conditions, the bottle is launched and flies into air. Investigate how the acceleration during lift-off depends on relevant parameters. So my focus point in here, I will talk about the relationship between the partially filled with water and acceleration. Also, I will try to change the different parameters on certain conditions to see the process during the lift-off. And here's my preliminary observation. As you can see that I used a simple experiment to try to do the water bottle rockets, and also use a tracker to analyze how the motion of rockets go. For updraft is about the velocity at the time, and for downdraft is about acceleration and tight relationship. Also, here's my crystal setup. In here is a launcher which I used to control the launch angle and the releasing timing point, so I can control air pressure or water flow in different experiments of different parameters. And for the bottle I used in here is with a bottle with 70 centimeters width and with a 72 grams weight, and of the nozzle is an 8 millimeters one, so I can control the same diameter, different parameter of my bottle. About air pressure, in here I use an automatic pump to control a different air pressure, so I can do a different parameter of my experiments. Also, in here I use my simulation to assist my experiment result, and for this is how my simulation mechanism works. You can see that I can change the different parameters in here, change the pressure, change the water flow, even I can change the bottle size. And for right graph is about my real experiment data and simulation relationship. So in here, in the same condition with the same parameters, for example, like the same water flow and the same air pressure, and try to overlay together, and since that there's very similar trend in here. So in a later discussion, I will use my simulation to assist my experiment data. Next, I'm going to talk about my qualitative flight process. So for first stage, it's about pressure. When I start to pump air in, it will call it pressure. Also, due to the equation of PV equals nRT, in the same condition with the same temperature and the same volume of the water bottle, when I keep pumping air into it, the pressure will keep increasing. Also, we will store the potential energy in the bottle and causing a force to the water surface. For the next stage is about frost. When the pressure causes a force to the water surface, the force will pass through the water. And when I release the rocket, the frost will eject, the water will eject at a very high speed, which means the potential energy will transfer into the kinetic energy of the water. Also, so the water bottle will, due to the conservation of momentum, so the water bottle will have a different direction of eject outs. And this is all my process during the water bottle eject. So the pressure causes a frost. When we release it, it will have a different direction and the water ejection. So you have this is all my 3 different stages of my qualitative explanation. And here's about the first stage about my different rubber flight phases. For first stage in here, I call it a lift off because when the speed is reached to the maximum speed, and this stage is called lift off. And for the right part is about a free fall state. As you can see that when the speed of a rocket is reached to the maximum velocity, it will start to decrease, and also the acceleration will start to decrease. So here, there are 2 parts of my different flight phases. But as a proper statement mentioned, to investigate the behavior parameters depends on during the lift off time. So in a later discussion, I will put my focus on the lift off stage. So next, I will talk about my quantitative rocket acceleration. So as a video, you can see that when I release a rocket, the water of the inside will eject at a very high speed. So I need to know how fast that the eject of water is. So according to a mass flow equation, I can know that in which time that the mass of flow of water will eject out. So also, knowing using the mass flow rate, I can use it to push the frost because the frost depends on water. So the equation of the frost is like this, and I can know that the frost is dependent on air pressure that I pump into a bottle in the initial statements. So after considering the mass change of rocket, I also consider air resistance, so I can get an acceleration of rocket due to this equation. And for right graph, in my first analysis during a rocket eject, for this part is just the water eject direction, so it will cause, according to the conservation of momentum, the water will eject out, and also the air resistance and the weight of my water bottle. So next, I'm going to talk about my different experiment to prove my assumption and my theory. I got 4 different parameters, and for the first one is about air pressure. In here, I think the air pressure is very important key parameters due to the equations of the frost, so I can know that maybe if I change the air pressure there has some different velocity and different acceleration. So in here, I've designed 4 different air pressure units: 1, 2, 2 to 2.5, 3, and 3.5 bar. And in here, I control the same water fill and same water bottle volume, which is 500 milliliters, and it's using the same release angle to see the different eject velocity and acceleration of these 4 different air pressure. And about my hypothesis in that, also just depends on the equation of frost. I can know that if I change the air pressure in the bottle, it may have some significant frost and causing the significant different acceleration in here. So in here, I'm saying that with a bigger air pressure in it, will cause a bigger frost, maybe you'll have bigger eject velocity and acceleration. Here's my 4 different air pressure results. So I overlay together and know that the bigger air pressure, like 3.5 bar, will have bigger you will have bigger maximum velocity in a shorter time. So for x-axis is about time, and for y-axis is about velocity change during the time go through. And for our next experiment is about water fill. Just as I mentioned, the water fill will also affect the mass flow rate in there. So I think there's also a key parameter to a water bottle rocket. So in here, I designed 6 different water fill in here, trying to compare the different velocity and acceleration during these 6 different parameters. Also, is my hypothesis know that due to a frost equation, you can know that the frost is also depends on the mass in here. You can see that dm to divided by dt. So here, with a different mass, maybe will have some different mass of water. There's a different velocity and acceleration. So this is my all 6 different results of water fill. So of course I overlay together to try to compare the difference of them. So as you can see that when a water fill is 75 milliliters, it will have in shorter time to reach the maximum velocity, which means that it will have the biggest acceleration during this 6 different water fill. And also with a 150 meter one, it has the smallest acceleration. For x-axis is about the time, and for y-axis is about velocity. And for that part, it's about the different water flowing to compare to a different maximum velocity. And you can see that according to the near line, there's the same trend in here, but of course it's not very similar, but I think it has the same trend. And for our next parameter, it's about different diameter of nozzle. So of course, also according to my equation of my frost, there's also the area of nozzle in my parameters. So here I try to use the K to adjust the diameter of nozzle. I design 6 different nozzles in here. I also use the same water fill and same air pressure to try to compare the different velocity and the acceleration. So in here, due to the equation, know that also the mass flow rate is also depends on the area of nozzle, and which means is the diameter of nozzle. So in here, I think maybe with a bigger diameter of nozzle, the water will eject out fast, but I think that there's a critical value between the diameter of nozzle and the mass flow rates. And here's my result of 6 different diameter of nozzle. And for the biggest one, which means the 1.6 centimeters one, it had a bigger acceleration during this process. And for x-axis is about time, and the y-axis is about velocity. So you can see that the 1.6 centimeter one is reached to the maximum, also have the biggest maximum velocity in the shortest time. And for right back about the different nozzle of diameter to compare to a different maximum acceleration in here. So for our last experiment, it's about the shape of my head, shape of rocket head. In here, I designed 2 different different shape of head. For the left one, it's about flat surface, and for right, it's about oval surface. And in here, I use the same water fill and also same air pressure to see the difference. And for my hypothesis, I think the most difference between these 2 shapes is the air resistance. Due to I consider air resistance in my equation, so I try to adjust the shape that contact the air, and I can know the air resistance coefficient by this equation. And here's the result of different shape of head. And for green point one is about oval shape, and for blue point is about flat shape. But it seems that although there's a little different, but it's very similar. So here I assume that maybe the air resistance is affect the free fall stage instead of the lift off stage. Next is about my conclusion. So about mechanism, how the rocket actually eject out is about I pump air into it, you will cause a pressure, which means you will store the potential energy in it, and after the release the rocket, the air pressure will push the water out and turns into a kinetic energy of water. And in the same moment, at the moment, the water will eject out and the water interior will eject out too. And this is the conservation of momentum in here. And here's my different reference parameters. For air pressure one, when the air pressure is 3.5 bar, it has the biggest aeration. And for a water field, is when the 75 millimeters one have the biggest aeration, and instead the 150 millimeter ones won't have the biggest aeration due to the mass flow rate. There's still water mass in the water bottle. And for my third parameters about different change a different diameter of nozzle, and know that with a bigger center diameter of nozzle, it will have bigger aeration due to the equation of my frost. I can know the area of the nozzle. And for my last one is about the different shape of head. In here you can see that I use two different shapes. One is the oval one, and the other is a flat one. And the comparison between this one is not very significant, but I think there's still difference between the due to the oval one has a much bigger air resistance during the survey. So the shape of head will affect the free fall stage the most instead of the lift off stage. And this is all my report. Thanks for listening.
Okay, so it's about time to ask a question.
Hello, I have some questions. First is for the experiment setup. Is the rocket made by yourself?
No, I saw bottom.
You can hold it.
Yeah.
Okay. And thank you. And second question is, your graph is made by the coding
Like a velocity graph.
of that.
Yeah.
And then next question is, when you do the rocket, you only set up one camera on the front, or you have set up another camera?
Set up what?
Only set up the camera. It's under the ground floor.
Yeah.
It has some height.
I forgot to see to activate the whole process, eject process.
So the camera is on the
Yeah.
And next question is, your first experiment is talking about the air pressures, right?
Yeah.
And how do you measure your air pressures? If
Oh.
you have a measurement?
I use an automatic pump, and it will shows how big the air pressure is on the
Oh, so it can inject by automatic?
Yeah, yeah.
Okay, thank you. And next is the experiment number 4, and it's talking about the nozzle radius, right? And is your
I can diameter one.
oh, sorry.
Yeah.
And is in the conclusion that is radius smaller and the velocity is higher? Is that true?
I mean the bigger diameter that will have the bigger acceleration.
Oh, bigger diameter will have the bigger
Yeah. So
acceleration.
maybe I have the same run in my conclusion.
Okay. And so in your theory, the momentum conversion is your main theory.
No, it's not main theory because it's just a phenomenon that will happen in conservation of momentum during this process.
Oh, so your force is not only about momentum conversion.
My force, if you mean
Rocket.
just the whole system, the water eject and the
Time's up.
water buckets.
So 3 minutes for the preparation.
现在也可以选哎，从那个抗死的地方 gap 开始也许。走抗死 gap gap 你可以进行一球。
Okay, hello everyone. I'm the opponent from Team TYPT, and right now I'm gonna reform the water of the battle rocket. And this is the problem statement from the reporter. Pump an air into a plastic water bottle, typically filled with water. Under certain conditions, the bottle is launched and fills into the air. Investigate how the acceleration during this depends on religious parameters. And this is the key points that reporter wants to search for. First is the energy transfer, and second is the air pressure, how to influence the velocity of the rocket. And this is the overview of the report. First is their theory. They use the ideal gas formula and energy analysis. And second is the phase. They separate it to two parts. First is the lift-off part and free-fall part. And they mainly analyze the lift-off part. And next is they analyze the parameters that affect rocket and present the equation. In order is the air pressures, the weight of the water in the rocket, and the nozzle diameters, and finally is the shape of the head. And in the experiment part, they introduced the experiment material, but didn't talk about how to measure very clearly. And next is the present a full data chart. And finally, consider an airport, diameters of nozzle, water field shape of the rocket that I mentioned before. And finally is their conclusion. The potential energy turned to the K is that the pressure from the air turned to the kinetic to the rocket. And the maximum acceleration of the effect of the air pressure diameters of nozzle water field shape of the rocket's head. And this is the remarks to the reporter. And first is the advantage. The speech is easy to understand and view very clearly theory. And they have shown the video of the experience that make us very clear to understand. And second is they do several experiments to find a relationship. And this is their suggestion. First is they didn't have complete experience between two or several parameters. And second is didn't explain the graph very clearly. And points maybe to be discussed. And in next discussion part, I want to discuss in separate for the in order is theory part and experiment part, and maybe have the how to solve the data. And first is the A in the formula of air resistance, and second is the formula accurate in high air pressures, and third is the force analyzation in the theory. And for the experiment part, I want to discuss first is the rocket design and the parameters of it. And second is to comparison of the experiments and the theory. And third is the way to collect the data. Thank you. So I want to invite the reporter. Okay, and first of all, I want to discuss the experiment setup part.
Yeah.
And I'm very curious about this. Did you control the mass of the rocket? Because that, for example, the experiment 4, you change the shape,
head.
the head.
Yeah. Oh.
If that will influence your mass of the rocket, do you
Okay.
agree this?
Yeah, I agree with you that during the different experiment you control the mass. But maybe I didn't show very clearly. I put the weight on the head part, so it made it become always be 72 grams. Yeah, so I didn't.
So you have control the mass.
Yeah.
Thank you. And then
So maybe I can show it. Yeah. So I will show it more here during next time.
And then second for the question for the experiment setup is so can I use the right mode?
Go ahead.
And because you have mentioned your camera is set under the front,
Yeah.
but the rocket is go from the vertical direction, right? But this will happen one issue that maybe this will have the vision error in your thing. So do you agree that will affect your experiment result?
You mean like the distance between where the two short will have some different
Yes, for
size?
example, like this way. This way. You see the angle in here is different. So in this, because the vision is not horizontal, so maybe it will influence your visual and make some error. Do you agree?
Yeah, I agree with you, but in my experience, I put it in far away so I can just check it out. Of course, maybe there's still some angles error problem, so maybe, yeah, I think that's very, I didn't mention it, so I think maybe next time I will try to put it out so we can see it all. But in my experience, I use a tracker to check it.
Oh,
Yeah, so I can adjust the. Like this one is the 1 centimeter. I can put in so the data will all can be adjusted. Yeah.
So you agree that maybe have the errors, but you think that maybe it will just affect a little bit.
Yeah.
Right?
Yeah.
So maybe we can even change this error.
That's fine. Yeah.
And this part is the theory part. And can you listen to the theory part from your leading equation? First of all, you have assumed the air from in this square is the ideal gas, right?
Yeah.
And in your equation, you have used the ideal gas equation.
Like PV equals
PV equal nRT, right? But right now, this has an issue that this equation only suits in when the air is the low pressure. Yes, low pressure and high temperature. But in your rocket,
Tell me about the low pressure and high temperature means. You mean the conditions?
yes, your equation only suits in that condition.
Yeah, of course. This is not ideal gas here, but I just try to describe that when I keep pumping the air into it, the pressure will keep increase.
Keep increase.
Yeah, so I think there's a formula that can fix the ideal gas equation, but I just use a simple ideal gas equation to describe the pressure that increases here.
Oh, so you just describe
Yeah, I just tell that when I keep pumping air into it, because in the same conditions, because the water won't be compressed, it will stay in the same surface, right? And so the volume and so of course the temperature in here I assume it's same temperature. So when the
Oh no, my name.
okay, you're something first.
Because my name because you use the ideal gas equations to quantify the air in this group, right?
You mean to measure how big a pressure is?
Yes, you use this equation.
I use the automatic, just a sensor to detect out how big a pressure is.
Okay.
Yeah, I didn't use that equation to measure how big a pressure is. Yeah.
Okay.
It just show it out from the automatic valve.
Okay, I understand. And but right now in your equation you have used the momentum conservation
Yeah.
to quantify the effect. But the momentum conservation only suits in the system doesn't have another force from another object, right? But in this case, you have get the force from the air. So how do you fix your equation?
About fixed part, of course there's the different force, but in here I use the conservation of momentum is I try to describe that when the water will eject out, and also the bottle will eject out up to just in okay. Because when this is a bottle and the water in here, and when I release it, the water will eject up very fast and in this way. And so the water bottle will also eject upwards. So I just want to try to use the moment conservation at the moment that I release the rockets and the water. Yeah, I just try to present the energy, the qualitative explanation. I didn't use it on my qualitative theory.
Oh, so can you explain how do you extend this portion in your formula?
About my formula, because in my equation I'm based on the force analysis, we can see that I draw different force and use the force to describe the equation. So maybe I can, because the momentum is equal to this. So I can maybe can know the mass change and also use the velocity change to have the same equation. But here I just want to describe the acceleration because the problem statement was the acceleration during the lift off.
Oh, okay, I see. And move to the next theory, I will be talking about say 16. And is this quite this is for quite this one you need to use this too many parts.
You mean this two line?
Yes,
Because I just want to see how the number of it. In here, you mean? You say these two means?
Yes, why you need to cast this?
Because I just want to see how big actually the force that push out is. Yeah, because then I think you will have because it's a different direction of rocket, so it will become a negative numbers.
Oh,
yeah. So maybe I can explain more.
And right now I want to discuss the experience part. So can you tell me, turn to page 24. And in this graph, did you compare the results with the theory?
Oh yeah, in here I said that because in here I changed the air pressure, right? And also in my theory I use the frost is equal to the tube pressure to divide the ATM and times in here. So I try to use this to do a parameter to do experiments. So yeah, of course, when a bigger pressure is, it will have much bigger force that the frost that can let the rocket eject faster.
And by experience, you find this the motion of the rocket. It isn't very simple. Can you give me some very potential parameters that influence the rocket didn't move
so okay, you mean like this line? Because this line is the So for this line is the near line according to my equation. So about like this part there is some difference. You mean why will have some difference?
Yes.
Okay.
Just give me some potential parameters.
I guess maybe the wind environment because I try to do my experiment in the indoor, but there's still too open and maybe there's still some wind effect, but I try to reduce it.
You try to induce. How do you induce?
Because
the wind.
Because the wind, because the rocket will fly very high, so I can't do it indoor. So I find a place which have this. There's a tube to block this, but the front and the back is still open. So maybe there's still some wind that maybe will pass over to it that affect my trajectory.
I see. Because the wind will affect by you try your best to reduce.
Yeah.
Okay. And can you turn to the experience that talking about the weight of the water? And can you explain? And in this case, this is the biggest velocity, right? And how many weight is this?
What I remarked about is the 75 one, is the purple one. Yeah.
It's the purple one. So
Have a maximum velocity.
but you see, this is 150 more in your velocity, but this is not the higher one.
You mean it either have a bigger velocity?
Yes.
So you want to know why it is? Okay. So in here, because the water will eject out. So in this condition, I assume that maybe there's still water inside the here that can eject out, and also because my former equation I have used the mass to consider a bottle mass and water mass. So when I increase the mass of water, the whole total mass will also increase too. So I think there's maybe a critical point between the water field in here.
And can you turn to page 29? Because it's actually has a deviation, and that's not a small number.
Mean like
Yeah, not a small number.
Yeah.
How do you explain this?
Because you mean like the near line and there's still
yes,
difference.
I think this is not a small number.
Yeah, because I think that's very huge number. And also, but the blueprint is my experiment, so like I said, maybe there's some wind effect, and also because the theory is too theoretical. And for real experiment, there's still other different parameters in lots of environments.
Okay, so I want to discuss your whole experiment part. And how many times do you do each experiment?
5 times.
5 times. Each experiment do 5 times.
Each different water field for 5 times.
And then I'm very curious about in your info. Okay, so thank you.
Okay, so 1 minute for the summary.
Okay, now right now is the summary of as per our discussion as points have been discussed. And first is the experience setup and how the result is measured and about the visual angle of the arc. And second is the accurate of the ideal gas TV equal nRT for the gas condition in the experiment. They talk about they just want to just a little bit complicated in the air. And third is the rocket movement connect with the formula. And fourth, we have discussed the graph connect with the formula. And fifth is the price of the graph in the air pressure in the experiment. And fifth is the why the velocity has a maximum value. And final one is the result compared with the theory. Okay, that's all. Thank you.
Okay, so it's time for the reviewer to ask questions.
Okay, first, to reporter, you consider it's a 2D or 3D motion?
2D. Because I just launched it 90 degrees.
First motion.
Yeah.
You may ignore, sorry, to opponents. You talk about the perspective of the camera well effect.
Yes.
Can you give me some suggestion about it?
Because I think in our market they have some kind of a camera can fix the problem dimension. So maybe they can try use that kind of camera to fix this problem. Or maybe like the reporter said, to set up the camera into the horizon of the motion of the rocket.
Thank you. To reporter, how do you know the? Oh, sorry. Is the diameter of the rocket body related to the accelerator? Both.
You mean the diameter of nozzle?
Yes.
Yeah, has high related relationship to acceleration.
And yes, I agree.
Compare the theory and the reality. Compare to the theory and the reality. What's the difference?
Oh, in my theory, I did add a wind effect on it. And by theory, I consider every system. So maybe just the environmental factor is the difference between the theory and the reality.
What wins effect?
Because the winds maybe will blow it at lots of weight, or if this way, maybe will let the acceleration become faster. And if the wind is this way, maybe will affect the acceleration to become smaller. But if maybe some wind is horizontally, it won't affect the acceleration not vertically. So, but I didn't very sure which kind of wind in my experiment is.
So in your experiment, does wind make the rocket more stable or vertical?
I think the trajectory of wind and rocket it didn't have. Yeah, of course it's a relationship, but I think it's not as stable. Instead, it makes you feel unstable because maybe it will affect by the wind.
Okay, time's up. So 2 minutes for the preparation. Time for the reviewer.
First, problem statement. Pump air into a plastic water bottle, particularly filled with water. Under certain conditions, the bottle is launched and flies into the air. Investigate how the accelerates during lift out depends on the relative parameters. Summary of the report, theory and explanation. Relation between the particle filled with water and acceleration. Focus on the thirst and Bernoulli laws. Clear about how the experiment and the setup. Experiment, a plastic bottle, thin at the bottom of the rocket. Launcher and automated pump. Reporter, pros, good explain about the theory and the experiment. Clear video about the water rocket. Using tracker to track the start speed of the water rocket. Have the good simulation and clear chart to explain what the experiment about. Consider about the air drag and have 4 types of air pressure. Clear result of the water fill and also similar to the theory. Cons don't have the video when a rocket reaches the top of the height. Some chart is not clear enough and didn't say what kind of the chart is on page 37 or more. Didn't talk about the angle and how rocket flew if I didn't ask. Summary about the opponent, theory and experiment. Focus on the energy transfer and air pressure. Talk about the A in the formula. Experiment. Focus on how the air pressure was measured. Curious about the mass of the rocket at the head of the rocket. Opponent pros. Clear point on the main focus. Clear chart about the overview. Talk about the theory and the concept clearly. Good control on time. Discussion about every part of the reporter and experiment and data analyze. Talk about the specific project on the chart. Consider about the time of reporter did the experiment. Cons didn't ask the shape of the wing and how it affect. Discussion about the experiment. Opponent says, have you considered about the mass of the rocket? And reporter replied, they did control the mass of the head and the bottom. In my opponent point is clear that the mass of the rocket affected a lot. Discussion about the theory. Opponent says, consider about the miss point in the reporter's PowerPoint. The air pressure is not fit in the theory. And reporter replied, I use automatic machine to measure the air pressure. And I think the reporter have a nice reply. But I think opponent really consider about this experiment and the situation inside the bottle. Thank you.
Okay, so I will run on the report from Team Bernoulli and not to have some remark on my report. So here I use a complete qualitative theory to talk about how the water exactly eject out and about energy transfer relationship. Also, I use complete theory and consider the mass flow rate and also to know the frost, and so I can know the equation of my acceleration during the time change and my water eject out. In here, I also analyze this in my force, and in here I use a different regime to describe how the process that ejection. Also, in here I use a launcher and a pump. And for a launcher, it's just I can control the limit releasing pipe. And for automatic pump, maybe I didn't say very clear, but in the pump it can show how big the pressure is in the bottle. And also I deal different parameters about air pressure and water field, diameter and also the shape of it, and try to compare them together. So about the graph meter, I didn't explain very well, but for most x-axis is about time, and for y-axis is about velocity. Because I want to see the velocity change during the time and to compare the acceleration. And also, I compare the experiment with my simulation and try to talk about to prove my theory and my assumption. Also, with a discussion with a product reviewer, both of them gave a very creative and constructive idea to me about the position of placing camera. So I think I didn't consider that, but in my experience, I put the camera very far, so I can consider it. And also the changing mask during the extract process, because I think it's all main very key question in here. Just the mask will keep the flow out. About reason of different about simulation experiment, there's the wind effect on it. In the 2D or 3D motion, in here about winds, in here I just reject out straightly. So I didn't consider 3D and about winds because I think the winds is the effect is on the free flow stage to control the fly out process. About there's a misunderstanding of the chart, and this is all my remark for my report. Thanks for listening.
Okay, so any questions from the jury?
Your theory about the mass and acceleration, you should provide mass versus acceleration.
I mean the water field.
Yes, water field. Yes. Mass of the water. Yes. There's a big deviation between your data point and the theory, right?
Yeah.
Did you consider as the dark devices, the pressure inside the bottle?
Will keep changing.
Did you consider that?
Oh, I have considered it. So
Did you include it in your theory?
no, because I have considered this point, but my simulation I didn't consider water changing, but I think it's very similar. But also in my experience, it's just 80% transferring to 100% of my water field.
So you only fill the water up to 20%?
Because my water bottle is 500, and the most most experience I use is 100 milliliters to change the parameters.
So you don't have an explanation for the discrepancy between theory and the experimental data?
No, I didn't mention it.
So any other questions?
Okay. Question for all three representatives. During the level of deceleration, the behavior of deceleration is continually decreasing or oscillating or something like that.
I think acceleration will have a maximum point and will study just decrease because the water is not ejected out.
Okay, so you think it's a continuous decreasing?
I'm
Up and down?
I just study that enough to keep studying this.
I think it's a decreasing.
It's continuous decreasing.
Yes.
I think when the rocket lifts up, the graph will be go up, but it's decreasing. It's like this shape.
So any other questions from the jury?
So can we go to slide 23? So the result you show here is the velocity.
Yeah, our y-axis.
Y-axis, that's the velocity. So how is it related to acceleration?
Because for this page, I overlay together, and because the point is this point is at when this reach the maximum speed, so I can know the time between it and also this to measure how big an acceleration is to compare it.
So go to slide 23 again. So there is a discrepancy between your theoretical calculation and the experimental results. So how do you explain that, or can you elaborate more about that?
In my presentation, I said the wind effect of first
When
reason.
you mean airflow?
Yes, and also the air pressure exactly will change during the eject process. But
So do you consider to conduct the experiments in calm weather or to fix the conditions? You mean airflow,
my wind,
strong wind?
yes, some kind of just to like a force that like an air resistance, some kind of like force. I didn't use the contact effect to explain this.
Okay. So No more questions? So if so, let's prepare for the score. So the score for the reporter, 6, 7, 7, 7, 8. Okay, the score for the opponent, 6, 6, I cannot see, 6, 7, and 7. The score for the reviewer, 4, 4, 6, 6, 5. Okay, so we finished the stage, so we have 50 minutes for the break.